Welcome to G Fun Facts Online. Let's start with a question. What lies in the vast, dark emptiness between the stars? If you're picturing a perfect, silent void, you're not alone, but you're also mistaken. That seemingly empty space is teeming with a complex and dynamic brew of gas, dust, and energy known as the interstellar medium, or ISM. This isn't just cosmic filler. It's the most important substance in the galaxy you've never heard of. It's the cradle of new stars and the graveyard of old ones. It's a cosmic tapestry that accounts for about 15% of all the visible matter in our Milky Way. And it's the stage upon which the entire cycle of stellar life plays out. Today, we're diving deep into this unseen realm to uncover the secrets of the space between the stars. The interstellar medium is a surprisingly diverse place. By mass, about 99% of it is gas, while a mere 1% is made of tiny solid particles of dust. But as well, see, that 1% plays an outsized role in the cosmos. Let's start with the gas. It's mostly hydrogen and helium, the original elements forged in the Big Bang. About 91% of the atoms are hydrogen, 8.9% are helium, and everything else, what astronomers call metals, makes up a tiny fraction. But this gas isn't uniform. It exists in different states or phases based on its temperature and density, kind of like how water can be ice, liquid, or steam. First, we have molecular clouds. These are the coldest, densest regions of the interstellar medium, with temperatures just 10 to 20 degrees above absolute zero. It's so cold here that hydrogen atoms pair up to form molecules. These clouds are the true stellar nurseries of the galaxy. Their immense density allows gravity to take over, pulling gas and dust together to ignite new stars. Some of these clouds are so vast, they contain enough material to form millions of stars like our Sun. Since molecular hydrogen is hard to see directly, astronomers track these nurseries by looking for other molecules, like carbon monoxide, which act like cosmic signposts. Surrounding these frigid nurseries is the cold neutral medium. It's a bit warmer, between 50 and 100 Kelvin, and less dense. It's made of individual, neutral hydrogen atoms. We can map this medium across the galaxy thanks to a specific radio wave it emits at a wavelength of 21 centimeters. Think of it as hydrogen's unique radio station, broadcasting its location to our telescopes. Next up is the warm neutral medium. As the name suggests, it's warmer still, ranging from 6,000 to 10,000 Kelvin, about the same temperature as the surface of our Sun. It's less dense and fills a huge volume of interstellar space, acting as a transitional zone between the cold regions and the even hotter parts. Then things get ionized. The warm ionized medium is heated by the intense ultraviolet light from hot, young, massive stars. This radiation is so powerful it strips electrons from the hydrogen atoms, creating a plasma. This ionized gas has a characteristic reddish glow, known as H-alpha emission, which creates some of the most beautiful sights in the cosmos, the glowing nebulae. And finally, we have the hottest and most widespread phase, the hot ionized medium. This is gas superheated to 1,000,000 degrees or more by the titanic shock waves from exploding stars or supernovae. It's incredibly thin, less dense than any vacuum we can create on Earth, but it fills enormous interconnected bubbles throughout the galaxy. Our own solar system is currently drifting through one of these structures, called the local bubble. These 5 phases aren't static. They are in a constant, dynamic dance. Gas cools and condenses to form clouds, which then form stars. Those stars heat and ionize the gas around them, and when they die, they blast the medium with superheated material, starting the cycle all over again. Now, what about that other 1%, the interstellar dust? It may seem insignificant, but this cosmic dust is a powerful catalyst. These aren't dust bunnies. They are microscopic grains of rock-like silicates and carbon, sometimes coated with ice. One of their most obvious effects is blocking and scattering starlight. Dust is better at scattering blue light than red light. So when we look at a star through a thick dust cloud, the star appears dimmer and redder than it really is. This is why the dense band of the Milky Way in our night sky looks mottled with dark patches. Those are vast clouds of interstellar dust blocking the light from the stars behind them. But dust does more than just block light. The surface of a dust grain is a cosmic meeting place, a platform where individual atoms can find each other and combine to form molecules. The most important of these is molecular hydrogen, the main ingredient for new stars. The formation of this molecule, and many other more complex organic molecules, happens on the surfaces of these tiny dust grains. Furthermore, when dust absorbs energy from starlight, it heats up and re-radiates that energy as infrared light. This allows infrared telescopes, like the James Webb Space Telescope, to peer through the dust and see the processes happening within, giving us breathtaking views of stars being born. Beyond gas and dust, the interstellar medium is also shot through with other invisible components. First, there are cosmic rays. These are not rays of light, but high-energy particles, mostly protons, that have been accelerated to nearly the speed of light. The prime suspect for this acceleration process? The shock waves from supernova explosions. These particles zip through the galaxy, acting as a source of heat and ionization, especially in the deep, dark interiors of molecular clouds that starlight can't reach. They are the high-energy wanderers of the ISM. The final key ingredient is the galactic magnetic field. It's incredibly weak, millions of times weaker than a refrigerator magnet, but over the vast scales of the galaxy, it's a powerful sculptor. The magnetic field is frozen into the ionized gas, meaning they move together. This field traps cosmic rays, forcing them to spiral along its lines and increasing their interaction with the gas. It also provides support to interstellar clouds, helping to prevent them from collapsing under their own gravity, which directly influences the rate of star formation in a galaxy. Astronomers can map this invisible field by looking at how starlight is polarized or aligned as it passes through dust clouds, because the elongated dust grains tend to line up with the magnetic field lines. So we have all our ingredients: gas in multiple phases, catalytic dust, energetic cosmic rays, and a guiding magnetic field. When you mix them all together, you get some of the most spectacular structures in the universe. Let's start with H2 regions. When a cluster of massive, hot, young stars forms, they flood their parent molecular cloud with intense ultraviolet radiation. This ionizes the hydrogen gas, causing it to glow brightly, especially in that characteristic red H-alpha light. The Orion Nebula is a perfect, famous example of an H2 region, a stellar nursery lit up from within by its newborn stars. This process is violent. The temperature skyrockets from a frigid 10 Kelvin to 10,000 Kelvin, creating a massive pressure wave that expands into the surrounding cold cloud, compressing the gas and potentially triggering a whole new wave of star formation. On the other end of a star's life, we have supernova remnants. When a massive star dies, it explodes in a supernova, one of the most energetic events in the universe. The explosion blasts the star's outer layers into space at up to 10% the speed of light. This ejecta sweeps up the surrounding interstellar gas, creating a shell of superheated material called a supernova remnant. These remnants glow brightly in X-rays and visible light. The famous Crab Nebula is the remnant of a supernova that was seen on Earth in the year 1054. These structures are not just beautiful, they are crucial. They are the mechanism that seeds the interstellar medium with heavy elements forged inside the dead star. Massive stars don't just explode. They also have powerful stellar winds, streams of particles flowing from their surfaces. These winds can carve out huge cavities in the ISM called stellar wind bubbles. When many massive stars are born together, Their winds and eventual supernovae combine to create enormous superbubbles, which can be hundreds or even thousands of light-years across. These superbubbles, filled with the million-degree hot ionized medium, can become so large that they burst out of the galaxy's disk, venting hot metal-rich gas into the galactic halo in what's known as a galactic fountain. This all feeds into the grand cosmic life cycle. It all begins in the cold, dense heart of a molecular cloud. Gravity pulls clumps of gas and dust together, forming a protostar at the center. Around this baby star, a rotating disk of material forms, a protoplanetary disk. Within this disk, dust grains stick together, growing from pebbles to planetesimals to full-fledged planets. This is how solar systems are born, from the raw material of the ISM. And when stars die, they return that material, now fundamentally changed, back to the medium. This is the process of chemical enrichment. The first stars in the universe were made of only hydrogen and helium. All the heavier elements, the carbon in our cells, the oxygen we breathe, the silicon in the rocks beneath our feet, were created inside stars. Lower mass stars, like our Sun, gently shed their outer layers in their old age, enriching the ISM with elements like carbon and nitrogen. Massive stars end their lives in core collapse supernovae, violently ejecting huge amounts of oxygen, magnesium, and iron. This process is a one-way street. With each generation of stars, the interstellar medium becomes more enriched with these metals. Our Sun and its planets formed from a cloud that had already been enriched by countless generations of previous stars. Without this cycle, without the interstellar medium acting as the repository and delivery system for these elements, rocky planets like Earth could not exist, and life as we know it would be impossible. The story of the interstellar medium is the story of our own origins. It proves that the cosmos is not an empty, static place. It is a dynamic, interconnected ecosystem. From the frigid stellar nurseries where stars and planets are born, to the fiery remnants of supernovae that seed the next generation, the ISM is the engine of galactic evolution. And even with powerful telescopes that can see across the electromagnetic spectrum, from radio waves to gamma rays, we are still just beginning to understand the full complexity of this cosmic tapestry. The iron in your blood and the calcium in your bones were once floating in the vast, dark space between the stars. You are, quite literally, made of stardust, delivered to you by the interstellar medium.